Hey, Sarah, how are you?
Good, how are you?
I'm very good, thanks.
Lovely to be here. So you're Tim, correct?
Yes.
Okay, lovely. Yeah, I've watched a few of your videos. They're fantastic.
Oh, amazing. Thank you so much. Did you watch Yannic's video on your
I
hardware?
did. I loved it. It was sufficiently grumpy, which I appreciated.
Amazing. Been so excited about having you on, actually.
Yeah, it was lovely to get the invite. I think it's a really fun premise of a podcast where you essentially choose an idea and talk about it. So it seems like you have really good banter.
Today we have Sara Hooker, who's a research scholar on the Google Brain team. She's training models that go beyond test set accuracy to fulfill multiple desired criteria: interpretability, compactness, fairness, and indeed robustness. Before being at Google Brain, she founded a local Bay Area nonprofit called Delta Analytics. She taught herself machine learning from scratch, and she helps to do the same thing for others. She started the underrated ML podcast with Sean Hooker, her brother from the UK. It's a podcast that pitches underrated ideas in machine learning. And you'll see a bit of a pattern here because Sarah is clearly concerned about myopia and tunnel vision and technological determinism in machine learning research. When Sarah's not smashing the machine learning game, she loves painting as well, by the way. But a little bit about her work. Sarah published a paper called The Hardware Lottery. She pointed out that machine learning researchers do not spend much time talking about how hardware chooses which ideas succeed and which fail. Sarah used the word lottery to mean that we are locked in by the technological decisions of the past. As time goes on, it's harder and harder to go back and change our mind. The opportunity cost between winning decision branches and losing decision branches increases exponentially with time, especially in the hardware domain, where billions of dollars of investment are needed to create new technology. Sarah believes that a breakthrough in AI is likely to require a new combination of hardware and software. So another one of Sarah's papers is on interpretability. It was called a benchmark for interpretability methods in deep learning networks. And she noticed that results across several large-scale image classification datasets show that many popular interpretability methods produce estimates of feature importance that are not much better than a random designation. And she came up with a much better alternative method. And also, Sarah's super interested in bias and compression. There was a paper that she wrote called Characterising and Mitigating Bias in Compact Models. And Sarah pointed out that pruning and quantization methods, which are important for storage and compute optimization of machine learning models in production, might actually trigger a hidden reduction in performance on certain categories of data. So, for example, low frequency groups, blonde males was actually given in her paper as an example. But we here at Machine Learning Street Talk are super interested in interpretability. So we'd love to talk to Sarah about that today. Also on the show today, we have MIT PhD Bayesian Keith Duggar. We have Yannic Lightspeed Kilcher, and we have Sayak, the neural network pruner, Paul. Anyway, Sarah, welcome to the show, and thank you so much for coming.
Thank you. It's lovely to be here. I feel like I should designate you to rewrite all my papers because you give it quite a bit of flair in your introduction, which is lovely.
Oh, thank you so much. I really appreciate it. So why don't you give us the elevator pitch on the hardware lottery?
So the hardware lottery at its core is really about how does science progress and what in the marketplace of ideas causes inertia. And inertia is all the things except for the value of idea that may amplify it or set it back. And it's called a lottery because really the idea is that there's things that are independent of the quality idea that may impact whether an idea is widely accepted in a community. And in particular, what I argue here is that for computer science, that is tooling. So that is our combination of software and hardware. Because computer science history is in fact very short. So the first realistic modern day computers were less than 100 years old. And over this less than a century, what we've seen is that most of the big swings in progress have been linked to a combination of the right idea at the right time. And the right time has invariably meant it matches the downstream compatibility of hardware and software.
I've had this question about it, and that if you read the paper, so it's part history, which is quite nice and thorough, and it's part kind of an outlook from you, or you propose this thesis specifically to hardware and also to tooling, as you say. My question to that is, what's so special about hardware and tooling? Because in a way, you could say that counts for everything. So if physicists, someone develops quantum theory, and all of a sudden, a lot of people go into quantum theory just because that turned out to work, or someone researches, I don't know, GANs, right? Someone discovered, Ian Goodfellow put up GANs, they tended to work a bit, and all of a sudden, there's like this massive push in this direction, which all of this is not necessarily hardware or tooling, but let's say ideas or techniques or so on. What's, in your view, what's special about hardware that makes this kind of ultra important?
I guess there's a few premises baked in there, so let me break it down. But I guess part of what you're suggesting is, so why does tooling play such a disproportionate role? I'm arguing that it does. Why? And then I guess implicitly you're saying there's a lot of things that can impact why an idea might be popular or chosen. So why focus on hardware? I think that like all choices in life, it's a product of what comes before. So it's not necessarily that hardware is the only thing that determines what comes next. It's almost like when we go for a walk in the morning, we almost set into action a set of consequences that are linked to our decision to leave the house. But within that, there's clearly some decisions that have a bigger impact in our lives than others. Like I mentioned, the idea of if you leave the house, there's a chance you get wet because it's raining, the small decisions of the everyday. And what I'm arguing is that hardware is more like the big decisions of choosing your job or choosing your life partner. Because within the framework of computer science, it has arguably determined at several juncture points what thesis of ideas survive and what thesis of ideas are neglected. And by that, in particular, looking at our own artificial intelligence history, we can see that hardware is really firstly disadvantaged connectionist approaches, which are now our widely used deep neural networks, and now really overfitted to these same approaches. And what I'm referring to is that starting in 1969 onwards, we had this push for general purpose hardware. And this is hardware where the goal is to take any piece of code and execute it. And this is what we know as CPUs. And that did not favor connectionist approaches because in many ways, the secret ingredient was the cost of matrix multiplies, which are hard to parallelize unless there's specific types of hardware that parallelize them well. And so with CPUs, researchers were never able to train networks that were deep enough. And this turned out to be the critical ingredient for empirical success of connectionist approaches. So you mentioned GANs, and there's a whole host of subfields within deep neural networks that only became possible to explore because in the early 2000s, we developed the right hardware combined with the right software ecosystem, which I also talk about. This idea that a lot of the early languages like Lisp and Prolog didn't work well with deep neural networks. And then we had a healthier ecosystem of Torch and Lush and then Theano, and then now the current generations of TensorFlow, PyTorch. All this meant that finally deep neural networks could break through. So to answer your question, I think that the combination of hardware and software needs to be talked about because looking forward, we're almost at a new cliff, which is what I argue in the second part of the paper. But it's something that I truly believe we need to be talking about more, which is that we now have hardware and software that has almost done a total pendulum swing and now favors these large deep neural networks. But we've become stuck in this research track of we're just throwing more and more parameters at the same model and the same architecture and hoping for different results. And in many ways, it has become very costly to stray off this formula.
I agree. As I said, the first reaction to this is completely agree. I think many of us have been in the situation where even in these early frameworks like Theano or early TensorFlow, you have some idea and then you just think, oh man, it's going to be a pain to write this in this framework, or that's going to be so slow because I need whatever, my sparse, whatever, and GPUs are crappy at sparse. All of this is clearly, and you have this very nice history, especially related to GPUs, right? That we have had CPUs, and then by mere accident, let's say, people love gaming. And through that, so much money has gone into GPUs. And then, yeah, by mere accident, we discovered we could use them for deep learning. And that sort of switched this paradigm around. So how do you classify the current rise of TPUs? Because, right, GPUs are almost, if you're still training on GPUs, you're last century almost. So now the new things are TPUs. How do you view the rise of TPUs? And how do you view, I know you are connected to Google, but how do you view Google's, let's say, almost monopoly on TPUs?
I guess there's a few questions baked in there again, so let me take it at the beginning. At the beginning, you mentioned this idea that I talk about in my paper, which is that GPUs are ported over almost as a fluke. GPUs were very much developed for gaming, and then in many ways we surreptitiously benefited. We figured out a way, and it was a fairly intense piece of software engineering magic as well. In fact, if you go back to the history of 2012, a lot of it was the sheer willingness to invest in the software that would work with GPUs, which is also interesting. But I think what is important about that, and a common theme in answering the rest of your questions, is that the hardware space is extremely small. And when we talk about the cost of decisions, it is the cost of making the wrong decision and the available choice at the time. And hardware has primarily, because of the sheer cost of both entering into the fabrication of hardware, as well as the need to recoup those returns, has centered on commercial end use cases. And in many ways, it is lucky that GPUs work so well, because GPUs were developed with a different end use case that was commercial, and we repurposed it for a research end use case. The availability to researchers of hardware that's developed with a research idea in mind is painfully limited. In fact, this is where I'll talk about TPUs, because TPUs are also designed with a commercial use case in mind, which is that neural networks have proved remarkable at performing in many different domains and on many different tasks, but have yet to translate into all these exciting use cases and all these exciting environments where they actually make an impact on real world problems. And TPUs were really designed to help unblock that. And you have variations of this, like the Edge TPU, which is really designed to make ML accessible in these resource constrained environments. You mentioned perhaps your grumpy side is that TPUs are Google specific. I really think hardware is very much, that community is very much geared this way. So Google's not deviating and doing anything nefarious. In fact, like, Google is very open source in many regards. Partly why I get to talk about my research and write the grumpy paper we're discussing today is it's very much open source first. But for hardware, and the hardware community has traditionally been very closed. And TPUs are one example of this very specialized hardware for commercial use of deep neural networks, but NVIDIA has their own, ARM has their own, Facebook has their own. And the common thread is that hardware communities don't publish, and definitely there's very few examples of open source hardware design. And the reason that is, again, going back to this cost of development. Machine learning community is in some ways exceptional because the pace of iteration is very fast. We have many open source conferences. We publicly talk about our work. And that's largely because we don't really build anything. So the timeline for us producing and reacting is very quick, which makes us more willing to share things. Whereas for hardware, the timeline is typically 2 to 3 years for development. You're looking at $85 million to $130 million. And the cost of being scooped is extremely high. And so that's what results in this difference of culture that you're remarking on, which also makes the premise of co-design very difficult. One of the main points I make in this paper is that partly what has made our search space so narrow and has really backed us into these hardware lotteries is that machine learning researchers have given up on influencing hardware because it's a different timeline and the ecosystems are completely different. I don't even speak in the same language as a hardware designer or even a compiler architecture. If you'll notice, look, I challenge everyone to read an ML systems paper tonight. It reads like the words feel oddly similar, but they use in entirely different ways.
I had a couple of thoughts on that. I mean, first of all, I'm interested in this sense that, in a way, theoretical computer science has already been completely divorced from the hardware, and we have complexity theory and we have lots of divergence between them. But I wondered whether you'd heard of this guy called Kenneth Stanley at OpenAI. He's written a book on open-endedness called Greatness Can't Be Planned. He's coming on the show in a few weeks, actually. And I would argue that the thesis in his book is closely related to yours, by which I mean he explicitly calls out the kind of convergent behavior of all systems, which is similar to your conception that we're locked in by previous decisions that we've made. And he says it's whether we see this in science or whether it's in inventions or education. And he calls out this kind of myopic and monotonic objective optimization obsession. He argues that there's a false compass in many ambitious search problems, which means we almost certainly need to do things which initially seem worse in order to reach a great stepping stone later. He argues that by doing a kind of objective-based local gradient optimization, as we do now, we'll always converge on basins of attraction and we won't discover new interesting stepping stones that might come later. So he says that great stepping stones are generally several steps away, and they can only be discovered, not explicitly found. So the story of GPUs and deep networks are just one of many possible stories of these stepping stones. So he says that innovation and stepping stones can go in all kinds of unexpected directions. A new algorithmic insight could instigate a new hardware in the future, but the reverse is also true, even though you argue that there's an opportunity cost. But that isn't exactly what's happening with quantum computing now. We know that it could be revolutionary, so we're investing in it heavily. So is this story unique to hardware and AI algorithms, or is it really just the story of all innovation? Every great innovation must wait for the right stepping stone to be in place before it can really happen. So for example, personal digital assistants, those PDAs from the 1990s like Apple Newton, it hardly made a mark and is mostly forgotten. Maybe the hardware just hadn't caught up to the idea yet. So a decade later with the iPhone, it did, and the idea really took off. So maybe personal digital assistants also depend on the hardware lottery, or maybe it's all just stepping stones snapping into existence and triggering their natural progeny when they do.
Yeah, that was a fantastic question, Tim. I feel like all your questions layer on this like history and context. I think in many ways, you're asking a few things, and that book sounds fantastic. I definitely, it sounds like I need to tune back in a few weeks. The question you're perhaps asking is, to what degree is this just a universal trait? And it is universal. I don't think there's going to be a time where we eliminate the hardware lottery, because really the hardware lottery at its core, even though I'm talking specifically about hardware and software here, is about inertia and the uptake of ideas, and on what causes friction in the marketplace of what is a good idea. What I do argue here is that the cost of friction is very high in computer science right now. And that's mainly because it's so expensive to jump between these basins. So a lot of how we clear the marketplace and correctly allocate value is by making it cheap and fast to compare. But right now, as a researcher, I face a dilemma. Even if I want to benchmark my algorithm against multiple different types of hardware, it's very expensive for me to do so. For example, I have to often refactor my code. It might take multiple days. I have to have the different hardware available. And this is within the small space of available hardware, because the real issue is we have a missing counterfactual of what hardware could exist. And we know from history and from these early examples that this counterfactual matters a lot. Like Charles Babbage and his analytical machine, it was almost a century later that the technology finally existed to really put into place the pieces that he needed to build his machine. And perhaps more importantly, I'm arguing that cost is becoming more pressing, because in many ways we're zooming in on the search phase. We're not enlarging it. A lot of these domain specialized hardware, which Yannic was talking about, and he mentioned TPU, but also really NVIDIA's new GPUs are ever more tailored to optimizing for matrix multiplies. And with these, we're essentially increasing the cost of deviating from neural networks in particular, and in particular from this format of having a prefix graph and having defined matrices. And I mentioned an example of one idea at least, which we can clearly see as having not benefited, and that's capsule networks by Jeffrey Hinton. Actually, Sarah Sabor, Nicholas Frost were on the first paper, and there's been a few subsequent papers. And I thought it was interesting because it was a different way of doing particularly vision problems. And I'm a big fan of ideas which take a stance in a kind of a grumpy stance, saying what is wrong currently with how we do things and can we fix it? And they propose some interesting ways of fixing some of the shortcomings of convolutional neural networks, but it was impossible to train. In fact, a whole team at Google tried to train these networks, and many people in the open source community have tried to train. And it's painful because capsule networks do this thing called squeezing. So they have periodic transformations that just don't fit into what we think of as just propagate forward activations, propagate backwards gradients. This idea extends optimization right now. You mentioned optimization and this idea of having these global updates. This is what I see as a major cliff with our current set of research approaches. We have centered on a network that treats all examples equally. So we tend to do full forward passes, and then we center on global update driven learning. And the difficulty of this is that it really is costly to expand the size of the network, because if you're doing a global update, essentially then your cost is the size of your network. And what is clear to me is that we're going to be facing a cliff where we cannot just keep on throwing parameters at this problem. The cost of training SOTA benchmarks is ever increasing. So GPT-3 just came out, and that cost $12 million for a single training. So the writing is on the wall. The question is, what do we do about it, and why are we not talking about it more?
From 2019, we saw a huge increase or a huge progressed research and development in the area of sparse neural network training and so on, which shows us a good promise of reducing the hardware costs and so on. So what would be your thoughts around that? I know you have got a paper on the state of sparsity in neural networks, so I really wanted to know your thoughts around that, which kind of takes us
what Sayak's talking about is actually a good example of what I would call a short-term lottery. Sayak is talking about right now for people working on compression, a lot of the most promising ideas for achieving higher level compression are not compatible. So we have unstructured sparsity, which is like removing columns from your house. Structured sparsity is like removing columns from your house, where you're removing activations. And that's what's actually commonly used in the real world now. Unstructured is like removing bricks. It achieves high levels of compression because you don't end up taking down the house. And theoretically, there's wide consensus that it's better. But it doesn't translate. Why? Because it's incompatible with current GPUs, TPUs, and it actually takes more memory the way that it's currently implemented in old versions of GPUs. That being said, what Sayak is talking about is that there's been a huge effort to update on a hardware level the capacity to handle sparse matrices. And in fact, the latest NVIDIA GPU, which came out, handles some forms of sparsity, but in parallel, there's also been an effort to handle very low levels of quantization. So train with bit quantization, which is very promising. So I don't see this as contradictory to the hardware lottery. I think it's an example of where there is a clear commercial use case for a research idea, there's momentum to translate it to hardware. And the pruning and quantization is a great example. I work in these areas because I really believe that in order to make ML accessible in resource-constrained environments, I grew up in Africa. So a lot of the places and communities I grew up in are extremely resource-constrained. Data is expensive. You can't charge your phone throughout the day. You may have limited battery power. If you have a smartphone, you're on earlier versions of a smartphone. And for these environments, and if we want to democratize ML, we have to think about compression. So there's a lot of people who are motivated by, in many ways, translating this idea. And it's already well established as the other ingredient that this is the way to go. We want unstructured sparsity. It's just better. How do we translate that to the hardware? But I would say the question still remains for the ideas that we don't have consensus that are commercially viable. And these are the big bets. And here is where it will not be solved in the interim by people stepping in and thinking about how to key to hardware to it.
Talking in terms of model optimization, which happens to be one of my favorite areas as well, there's this thought around the interpretability aspects of these different model optimization methods, such as pruning, quantization, knowledge compression, early exit, and whatnot. So what would be your thoughts around the interpretability aspects around this different optimization topics? Because there's evidence that suggests that the interpretability side of things often gets, compensated when you try to compress a model too heavily, or you try to prune a model too heavily.
I think your question there is, as we prune, how does that impact these other properties that we care about, one being interpretability? So I guess my recent work has looked at this through the lens of what does a model forget, but it actually has a wider takeaway, which I've been thinking about recently, so I'll share it here, and I'll see how much sense it makes. I'll beta test this insight with all of you. My recent work looked at, as we prune, what does the model forget? And what does the model forget, meaning what is the subset of examples that the model, when sparsified, tends to deteriorate performance on? Because what we all know is that overall, top-line metrics, pruned models show a remarkable ability to retain performance. And in many ways, other compression methods as well. You mentioned this idea of like teacher-student, quantization. The top-line metrics are preserved. But these are radically different structures. You can have 10% of weights, which is still performing at the same amount as the full 100%. And these are a difference of millions and millions of parameters. So the question is really, what are we giving up? How can we have such radically different structures that perform the same way? And what we find is that what you give up is performance on the long tail. And here's where I'll segue to my beta test. I think what this is really telling us, in other words, is that the majority of parameters in a network are used to encode in a very costly way low frequency instances in a distribution. And that is interesting. Why? Because when we think about it through that framework of you have a small number of parameters which can encode the mode of the distribution, the high frequency attributes, but most of your capacity is being used for this long tail, the question inevitably becomes, why don't we just treat the long tail better? Why don't we leverage that knowledge to use less capacity? And I think that this is a shift that I hope is coming in research, where we've treated the model as fixed, and we've essentially treated the data set as fixed. And a lot of the research has been around how do we alter the data set while preserving top-line metrics, given the same treatment of you have your standard epoch and batch size and whatever. And I think what these insights suggest is that we could get a lot more clever about how we treat the long tail during training to avoid using all this capacity to begin with. And there's some interesting arcs of questions there. But that's been a lot of my recent work on this topic.
This is fascinating to me because one of the biggest problems with machine learning is this obsession with accuracy. And there are so many other facets of behavior in a model that we should introspect about. And I think no one is really thinking about what happens when we prune a model. And I think this conception that you just said, that you're training for the long tail and that's what you lose when you compress a model, that's absolutely fascinating. But it does rather bring me to something else, actually, because you mentioned in your paper that there's a cultural divide in machine learning. And I read a wonderful article by Max Welling, which you cited, do we need more models or more compute? And he says there are many different schools of thought on machine learning, like white box versus black box, or symbolic versus statistical, or model driven versus data driven, or discriminative and generative. And he believes that custom hardware and computation is one of the fastest ways to improve AI. I think that's why he works at Qualcomm. And he's a strong proponent of deep learning. So this isn't an invitation for Gary Marcus to come in and criticize it. But anyway, but we're all talking about this article from Rich Sutton, which is the bitter lesson. Do we need massive amounts of compute and data? Because you're just saying that actually most of the information is on the long tail. So Rich Sutton said that we should stop trying to build overly simplistic models and instead rely on massive amounts of compute. He cites Deep Blue and AlphaGo, which is brute force searching and learning. And he's basically saying that human strategies for building machine learning models are always going to fail. So is this the only way forward for us?
Yeah, I love this question because really Max and Rich Sutton are they're two fantastic blog posts. I suggest everyone go out and read them. They're also fairly short, but they're really capturing a really fractured ecosystem right now of people who are thinking about this in different ways. So Rich's thesis, I would say, is throw more parameters at the problem, focus on what is tailored to current hardware. This is what has worked in my experience. Max, on the other hand, is saying your prior has to matter. So we know that particularly if you have more limited data, we know that you have to care about the assumptions you make about that distribution. And what Max didn't say in that article, but is really my concern about the rich approach and why I suspect in the long run it won't work, is that we also clearly just can't throw more parameters at the problem. It's just, I think this is a fact often goes unspoken, but we're in a regime of parameters, a very self-contained tasks. We're doing well at perhaps modeling a subset of human traits, but we are nowhere near the regime of human intelligence, but we're using so many parameters already. So this idea that we're just going to keep on scaling the number of parameters when we already see decreasing returns, but already having to use more and more parameters for every slight increase, it's almost, I phrase it as we're building a ladder to the moon. So this is a cliff. And I think what's interesting is that there's not many people who are talking about the fact that this is not sustainable. And it goes a little bit further, right? Because in many ways, whenever you're justifying doing something, what is available to you are the counterpoints of other ways to do the same thing. So deep neural networks are the first, in many ways, computer science approach that has broken through in a lot of these tasks. But we have biological counterfactuals that suggest that some of the assumptions that are embedded into deep neural networks clearly have deviated and are very costly. One I mentioned earlier is this idea of the global updates, where you update all the weights. And so that in many ways is your upper bound on constraint, because you need a hardware that will store all your weights, or you need ways to distribute these updates in a way that is quite costly. In comparison, our own intelligence is based on local updates, which surface into these global signals. But our hardware right now is miserable if you want to try and do local updates and computations. It's not catered well, nor to Yannic's earlier point about software. Software really disadvantages any type of local update computation. You don't have the inbuilt frameworks to think about it in an efficient way. And the other counterpoint is that our own intelligence, because of these shortcuts, because of staying local and also not processing all examples equally, is already far more efficient. Our brain runs on the energy equivalent of an electric shaver. Whereas if you compare it to the regime of parameters we're currently in for deep neural networks, it's bonkers. We're using the energy equivalent of thousands of flights to train a single model, and yet we're still throwing more parameters at the problem as a solution. So I suspect Rich will be proved wrong. This is my perhaps cheeky bet for the next few years. And it's mainly because it's going to become clear that the returns that we're getting are nowhere near the progress we need to switch lanes. It's very clear there needs to be a lane switch to a different paradigm for us to see a big increase in performance.
It's quite interesting that in your paper, you contrast some of the differences with the human brain, right? You say that it's just 1,400 grams of tissue and it's got 85 billion neurons, and it only requires about the same amount of energy as a shaver. But it also has some interesting properties, as you say. It doesn't suffer from catastrophic forgetting, and you don't need to back propagate through the entire brain. There's like localized processing. But coming on to, you're talking about Max Welling, and he's famous for creating these inductive priors in models, which improves the sample efficiency problem apart from anything else, because it means that you don't need to see as many examples of something if you can have a useful inductive prior. But there's also this concept of generalization, because surely the reason why we need this long tail is because we have to precisely identify every possible permutation of something. So do you think some combination of inductive priors and improvements around generalization could save deep learning?
Oh, so that was both a very sweeping question and a very specific question. Yes, so I do think we have to treat the long tail differently. So right now, the setup of a deep neural network is that all examples are treated equally. You do a full forward pass for all examples, you do a full backward pass. Each example is seen the exact same number of times during training, and you have random shuffling. So this prior essentially assumes that every example is equally special. And we know that's not true. In fact, what do humans do when we're uncertain about an example? We tend to move forward in space. We tend to squint. We tend to zoom in on an example. These are all biological mechanisms we have for reducing our uncertainty by essentially upweighting that example and inspecting it further, spending more time on it. Those mechanisms are absent in deep neural networks. And in fact, part of what I'm arguing is that parameters are compensating for that. The work I did showing that when you lose 90% of weights, what you lose performance on the long tail is really saying in different words that we are essentially spending a ton of parameters encoding and memorizing this small percentage of the overall data set. So why are we doing that in the crudest way possible? Can we change the training optimization process itself so we better treat these examples so it doesn't have to be weights bearing the brunt cost of this uniform treatment? And that's where I think it might get interesting. And it is related to Max's idea of inductive biases. I am more firmly in his camp. I'm not a Bayesian, so I won't go that far. But I will say that it is very clear that our priors right now are so essentially put so much shift the burden so much to the parameters. That is why we need these very oversized models. And we can afford to build in some better priors and assumptions about how we treat data to save us some of this computational cost.
To that end, on mitigating some of this over-parameterization, do you think sparsity-based training could be a potential solution? A step toward some, lesser parameterization, but more efficiency and so on?
Yeah, it's interesting. So you're bringing up this really exciting direction, model compression research, which is starting sparse. So it gets this question of why do we need to train this over-parameterized network in the first place if we can then reduce it through iterative pruning? Why can't we just start sparse? So within this, a lot of work is focused on things like initialization and the weight distribution at initialization that's needed. I think this is a very exciting direction. I would suggest that people have been looking at it too narrowly. I think, again, the interesting thing about this premise of starting at initialization is that I actually believe it's about, and this is where I will bring in Yannic point again, that so I talk a lot in the hardware lottery about the hardware and software stack, but even if we just look at algorithms, I would also say that there are some choices we made along the way that have disadvantaged certain ideas and upgraded others. And I think architecture design is a great choice. So architecture design has been a heavy research period of about 10 years now, from 2012, now we're in 2020, and it's all been around dense networks. And so in some ways, I think an exciting area of research, the initialization is one part, but I would actually suggest we take a wider view. What are all the choices we've made in architecture design and optimization that have disadvantaged sparse networks? Because really, a lot of what I suspect the difficulty has been around this idea of gradient flow, which used to be something that we talked about a lot in early deep neural network stages, because that was really an affliction of dense networks. You had really poor gradient flow, you had saturation of gradients, and then we introduced all these things like activation functions and batch norm. And with sparse networks, I think we're back to gradient flow issues. And so if we take a wider look at it, weight distribution is one, but weight distribution is really just capturing the weight distribution you get after you solve for gradient flow. And that's why in many ways, people talk about this hack of resetting after 3 epochs to that weight. I think if we think more about what are the choices we've made based on a distribution that is dense, can we rethink this formulation now for a distribution that is sparse? I suspect some exciting ideas will come out of that. And I think researchers are starting to think more broadly than just the weight initialization, but also these components along the way.
Yeah, to that end, I also think this has got a lot to do with the technical debt that it brings, because if you see something called block sparse matrices were proposed by OpenAI in the year of 2017. And clearly in 2020, we do not have any frameworks that support it quite well. And we do not have any hardware support for that quite efficiently. So recently, folks at Hugging Face started to talk about block sparse matrices and so on. But clearly enough, we do not have any major frameworks that support it quite nicely. So yeah, I definitely think the tooling around sparsity would need to be improved quite a lot in order for us, the researchers, to be able to pursue it in a more stronger way, I would say. And my second assertion would be, an interesting research question to pursue would be, what if we could design architectures that are probably freer from inductive priors? Because if you consider raised nets or any other deeper nets, they have a lot of inductive priors baked into them. So a good question to pursue or explore here would be how can we design efficient and better architectures that are freer from our inductive priors from the domain and stuff like that?
Yeah, I 100% agree.
The block sparsity, I think, or sparsity in general, is a good example of a technique that maybe right now is right at this edge. Because if I understand your point from the very beginning correctly, something like hardware is just so expensive to go back and rethink that often right now we're giving up, we're locked in. Sparsity, it might go the same way, but still we're early enough that we can say, wait, there is potential. And so we might build a bit of hardware. And there we see ahead a little bit. But in capsule networks, maybe that's already gone. And I'm plagiarizing like a Reddit comment I got a little bit that said, actually we're trying, as humanity, we're trying to solve this intensely complex problem of allocating resources. Because imagine the whole gaming industry invested, I don't know how much, $100 billion into GPUs. And now we have $100 billion worth of development. You talk, maybe this is to like the last part of your paper, where you have an outlook and you suggest maybe we should think about funding more of different hardware. But you also immediately put the counterpoint, which is that, look, GPUs are one direction, but right now there are maybe 100 ideas for new hardware. So even if we took all the money that went into GPUs, all the money that gamers spent, and allocated this to other, we still would only make 1/100th of the progress. So even if there was a hardware direction that would beat neural networks, would be or would develop capsule network hardware or something very esoteric that is just way better, we still wouldn't find it because we'd get 1/100th of the way there. Either that, or you have the super oracle telling you, yes, this very obscure direction right here is going to be the correct one.
Yeah. No, Yannic, it's a really good point, and I like it a lot because I think, so at the end I do say, perhaps you can research these different hardware directions. I actually am not, I would say out of all the sections of the paper, that particular paragraph where I talk about the hardware exploration, I'm still marinating on it because in some ways the question of allocating resource, which is what you bring up, is this question of what are my hypotheses about a space? And hardware, we're kind of running blind, right? So I mentioned some interesting directions there, but they're all very early on. And in many ways, the cost of exploring them is enormous. And so particularly when governments have to decide how to allocate R&D budgets, it's very difficult to allocate when your hypotheses in some ways are so initial. And it gets back to this idea of our discussion about sparsity, even in this chat, has been so well defined. We've talked about exactly what's wrong with hardware. We've talked about what needs to happen. Partly that is because hardware here cares quite a lot. And why does it care quite a lot? Because sparsity is commercially viable. As soon as we move away from ideas which clearly have commercial end impact, we run into this murkiness, and we run into this murkiness of what do we take a bet on, and it's so expensive, and how do we do it? And what is missing there, and what I argue in that latter part as well, is that it's actually software initially, which I suspect has to step up. Right now, I don't think about hardware in my day-to-day. I take the hardware I've been given, it's a sunk cost, and I go about my research problems given that hardware. To change that, I need to be able to deploy to different types of hardware in an easier way. I need better feedback loops. I mean, everyone who is here, I sense I'm talking to Yannic, you mentioned your frustrations at coding something. So I sense I'm talking to a fellow survivor. When you get these odd compilation errors that echo up from hardware and you have no idea what to do with them. So we need better as well, just feedback loops from how our algorithms translate. And that, in some ways, is the first step to having a better hypothesis. Because right now, to your point, I'm not sure we have an informed way to invest in new types of hardware. In fact, after this paper was released, I had conversations with a few people who reached out, and that question to me was, we want to design 8 different prototypes of hardware. What would you suggest? And I said, I have no clue. This is part of the hardware lottery. This is exactly what I'm talking about. And to mitigate that, we need more quicker feedback loops to understand what's not currently working. Because for Sparsity, if you saw my conversation with Sayak, it was very, very directed. We both agreed on what was missing. We both agreed on what were interesting future directions. And a lot of that is because that is an area where there's a lot of hardware architects who are also focused on it. And why? Because it translates to end impact. And that's not my concern in the hardware lottery. My concern is the areas that we don't yet have the hardware to see as success or failures. And that's where the problem is.
I've got a few thoughts, because I know in your paper you argue that there are so many future hardware directions that we haven't explored yet. You mentioned optical and neuromorphic computing and quantum computing. And you might argue as well that if you look on the motherboard in your machine, there's actually quite a diverse set of hardware that isn't a CPU. But one way of looking at it is that a typical computational graph, it could represent almost any type of computation. And maybe there aren't actually that many types of hardware out there to be discovered. Maybe you give the example of neural networks. So what they needed was a massive degree of parallelism. And I think Hinton even made that paper in 1989 saying that they needed parallelism. But the thing is, as Yannic pointed out in his video, it's very difficult to do neural network programming. Actually, they're annoying, right? Because they're unreliable, tricky, poorly understood. The training data, I think, was quite important. Because it's not just the hardware. I think they invented ReLU as an activation function and batch norm. And we suddenly had all of this data come at the same time. And there were quite a few things that happened to make deep learning take off. Because you mentioned capsule networks, I would argue that doesn't really require a new paradigm of computing. It requires sequential processing. And I don't really think any hardware would help you with sequential processing. And I suppose it's coming back to that stepping stones thing. There's a lot of serendipity. If you ask any successful person, how did you become successful? They will say, oh, it was quite serendipitous, actually. I just did this random thing and that thing led to another stepping stone. And one way to look at it is it's just stepping stones are discovered when you have all of the right environmental conditions. It's the appropriate time, then they get discovered.
Which is a lottery, right?
Is that a lottery? Is it a lottery or not?
Yes.
To quote my lab mate this morning, I talked about this paper, and he said, if the Greeks had GPUs, they would have done neural networks, which I'm not sure about, but.
Yeah, I would argue it is a lottery, mainly because of course, the person who ends up benefiting is like, oh, it just happened. But the people who came before just didn't know that it could happen. And in many ways, it's the size of the lottery that matters, because this happens on all levels. So it's how much time it takes to correct for that is the real question, and determines what we should pay attention to. And I would say that at an algorithmic level, we have the most flexibility in terms of iteration speed, joint information, because we release a lot of our work. The bottleneck is really at the software and the hardware level, because that is where there's the most inertia. And it's also where the communities have developed in entirely different ways. So hardware, I went to a hardware conference earlier this year where you could still go to conferences back in the era where we were all jointly together. It was in February. And what was fascinating was that many of the speakers who went up were trying to figure out what researchers wanted. And I was one of the only researchers there. And there was even one speaker who said, and now I want to invite researchers up, tell us what you want, because they're equally paralyzed because the form of training is entirely different. So we're not training hardware designers and machine learning researchers, and we're not doing any type of joint training. So the last hardware class that most of my colleagues have had was probably compilers in that undergrad CS program. But this is not creating a foundation. When we talk about national strategy, which is something that I only briefly mentioned at the very end of the paper, but a lot of technological progress is actually set at a national level. So for example, in terms of AI history, a lot of my directors and the people who are very senior within my org are all from Canada. And the reason being that Canada is literally the only country that consistently funded AI throughout the two AI winters. And the experts on neural networks all emerged from Toronto, Montreal. And this is, in many ways, this is a national policy which guided a sequence of events. Meanwhile, the UK and the US fairly rapidly abandoned AI research. And in particular, DARPA funding was very important for the US, and that cut off after in the late 1970s. But these are national policies, and they've determined huge chunks of computer science history. If we think about the last century, which is really computer science history, those choices have had ripple effects of 30 plus years. And even now, the most senior talent in our field is from Canada. And you can extend this because right now the question, getting back to this idea of hardware, is about funding. Who funds? And how is that knowledge shared? And what is the focus on? And implicit in part of what you were mentioning, Tim, is this idea of materials. So like, how much flexibility do we actually have at the hardware level? So part of what determines that is the materials that we use, and also the degree of exploration with those materials. But these are long-term processes. If you're thinking about designing a radically different type of hardware, like revisiting the premises themselves, you're talking about 20 years. And that's where it becomes not a corporate level investment, because there's few companies that can sustain that level of R&D. It becomes about a national conversation over what is interesting and important, and what are the big bets that nations want to take a part in. Returning to the training, it's very important that when we think about these different ecosystems and how isolated they are right now, at a national level, that's also a national decision. How does training happen? And where do we invest in programs? And that's also a crucial part of this, because if ML systems expert was on this call, we would probably very generally agree on the same problem. In fact, most of the reception I've gotten for this paper has been from ML systems people, all on LinkedIn, by the way. All hardware people are using LinkedIn, all ML people on Twitter, which is another fascinating difference. But we would talk about it in very different ways, which is part of this gap.
And so there are a number of initiatives right now that use machine learning, that use deep networks to design better hardware. I think it would be very ironic if deep networks were to be the ones that, not human communities, but the ML deep network community were to develop the hardware that ultimately replaces deep networks.
That would be hilarious.
Would just be a bit of irony.
You said in your paper that we've had the lost decades before neural network research, and we already had all of the knowledge on neural networks, but they were intractable on the hardware we had. So we missed out on this huge revolution. But just to be really cynical for a minute, I'm sure Gary Marcus is watching this and he's saying, no, actually, we're going to look back on this time as being the lost decades because we were so enthralled with deep learning. We completely stopped exploring other fruitful avenues. What do you think about that? Because as you say, it's all about what we pay attention to. And if all of our attention is focused on exploiting what we have with deep learning, and of course it's leveling off a little bit, as you say, we're not really exploring new ideas.
Yeah, I don't disagree. So I think that's a great rounding off question. So I actually don't disagree with Gary. In many ways, what I'm suggesting is that there are these pendulum swings, but the amount of time for each pendulum swing is determined by the stack. So it is your downstream choices which have determined the length of time of these swings. And I think part of my grumpy assessment, your excellent question about rich versus max, is part of my grumpy assessment is that this particular pendulum swing is also going to be determined by hardware and software, but also the limits of our hardware and software, because our algorithms that we've chosen to use are so computationally expensive. In order to delegate representation to the model, we've essentially thrown capacity at the problem. And that has had breakthroughs, but clearly we need to revisit some components of how we throw capacity at the problem. Do I think that's symbolic? That's a grumpy no. So I think what's interesting is that we need to prod Gary and ask him to specify symbolic a little better. He throws around the word symbolic quite a bit. I think I like Max's terminology better. He talks about priors, which is actually a different notion of talking about what symbolic AI is. It's the presumption that you engineer some embedded constraints based upon your knowledge of what the function space eventually should be. And that, for me, makes a lot of sense as the next direction, is that we're going to revisit how we treat examples. I think that is a very exciting direction of research.
But is it possible that it might have nothing to do with hardware and software at all? Because you cited the example of valves, right? People spent 10 years creating valves. And then when we had valves, people figured out we could use them for computers. It's a similar story with the engines on aeroplanes, right? They were invented completely separately and then they were used on aeroplanes. And similarly, there might be someone working on some kind of biological computation or something completely different, which might then be useful for AGI later. And by having this kind of paradigm or frame of reference talking about hardware and software, we might be just completely off-piste and we might be somehow creating a self-fulfilling prophecy around some deceptive idea.
Well, I guess what you're saying is, will you call me back in a few years and I'll come on the show and you'll be like, oh, you were off your rocker? It's always possible, but I think history of computer science is short, but I think what it tells us is that a lot of inertia is baked into what we choose to use as tooling. So I'm going to stick with my bet for now that it is tooling that will determine the speed of iteration. And mainly because if you think about it at an algorithm level, we're fairly nimble. We publish 3 times a year, sometimes more. Like, our ecosystem is moving very fast, and some would say too fast. The trickiness is in the tools we have to use to navigate some of these ideas.
That's right. But I think that the key point you're making is that we don't have agility on the hardware because of the opportunity cost. But that's mostly expressed in situations where there is not a direct optimization towards a known return on investment.
Fair. I think perhaps what you're saying differently is because researchers have so much focus on deep neural networks, maybe we haven't put forward an idea where there could be hardware oriented around. So that's also true. I hope that we will, there's always a feast and famine period in research. This is well documented. So when there's a feast, which is what happened in 2012, there's a huge effort to be part of that. Like, people want to essentially be part of a wave of ideas that move fast. And famine, people start taking more risks. And you can see it. The Bayesians are all emboldened lately. They're all pronouncing various degrees of critiques about deep neural networks, saying they weren't quite the way. The causal framework people, that tribe has come out and they're like, oh, we need causal analysis. So you can see there's always these waves where essentially the people who were before ostracized are given renewed attention. And that's mainly because the feast is over. We're talking about, okay, there's clearly a limit to this approach. What were those rogue researchers talking about? Oh, their variational dropout, which, by the way, is awful to implement. But people start reconsidering these ideas once it's clear that there are limits to the current approach. And that is slowly, but it does happen.
Amazing. Let's use this as a segue then to talk about your paper where it's called Characterising and Mitigating Bias in Compact Models. So when you compress a model, the behavior changes in a very unexpected way. So give us the elevator pitch on that.
So that work is joint with Yannic Morosi and some of my other colleagues at Brain. And that work is really interesting because what we do is we ask I talked about how pruning disproportionately impacts the Longtail earlier, and fairness often coincides with treatment of the Longtail, and that's mainly because fairness, partly what is concerned with is when under when protected attributes end up underrepresented in the data set. And why does that matter? It's because a lot of our parametric models are essentially frequency counters. Essentially, parametric models encode features which are well represented better and less represented worse. So when we talk about the model itself, what's interesting is that things like racial disparities in performance, as well as we've had well-documented cases of better performing on images from certain geographical regions, but not recognizing, for example, in very popular open source data sets, we have things like the groom class, and a Western groom may look very different from a groom in a different region of the world, and different ability to perform on these very different distributions. So a lot of the conversation about fairness and bias up until very recently has focused on the data. It's all been a problem with the data, a problem with the distribution with the data. And in many ways, what is interesting about this particular project is that we're asking what prior does the model itself bring and how it treats the data? And in fact, do you amplify bias by choosing a certain representation to encode your data versus another? And Sparsity is an excellent experimental mechanism to investigate this, because really what we're doing is we're varying precisely the amount of sparsity. And at every step, we ask, how is this impacting the long tail of the distribution, in particular, the presence of these protected attributes in the long tail? And what we find is that the choice of model is very important in how you think about fairness. And in fact, what we're saying is that sparsity, while you compress, you're disproportionately impacting this long tail, and it amplifies your bias if your protected attribute is underrepresented.
This is something I think that many people would agree with it intuitively. If you had to train, let's say you train a bunch of humans for your big concert event, and you just tell them what they look for. Have you ever seen this video where this guy checks for weapons and he barely touches the human? Like, it's okay, you have 1,000 humans to instruct. It needs to be really simple. So you just tell them, okay, do this. I think that this notion, it makes a lot of sense. And to investigate this, I think also makes a lot of sense, that if you have less parameters, then what you're going to fail on is the things that happen less often, which of course impacts, if you are in the group that happens less often, impacts you drastically. I think the question I would pose is, you said yourself, it amplifies bias. The question I would pose is, now that we know this, what is the good thing, or what is the best thing to do? Would you rather invest resources in, let's say, countering that bias now that you know how it comes about? Or would you rather invest resources in eliminating it altogether by going back to the data set? Because I'm picking you up on saying people have thought it's the data set, but we also have the algorithms. But I'm countering this to you saying it amplifies the bias. So wouldn't the investment be, let's go back to the data set now that we know that it's even worse if we sparsify?
Yeah, Yannic, I think fun point. I put differently, what you're asking is, so we find that the choice of model itself brings something to the table, and the introducing sparsity in particular amplifies the bias, but the bias is there even with an over-parameterized model. And I think that, but I guess you say if the goal is to eliminate the bias, where do you start? I guess it's interesting. So bias, particularly in these parametric models, is not eliminated, it's redistributed. So I think what's interesting is how to go about redistribution, which is a valid question. The big tricky part, and so why I like this paper a lot, is that a lot of fairness literature has assumed that you have access to the labels of the protected attributes. And so you assume that by some miracle, you have all your protected attributes labeled, and then you can measure the bias, and then you can assess it and iterate with how you either change the model itself or you change the distribution of the input data set. As we all know, in the real world, this is rarely possible. So firstly, many of our data sets are not labeled, but secondly, these protected attributes are particularly tricky to label. It's very sensitive sometimes to ask people what are their demographic attributes. And in fact, it's illegal in some countries to do. So partly why this particular work was really interesting for us was that by looking at what images are impacted, you actually come up with an unsupervised way at test time to surface the subset of data points that need further auditing by the human. And this kind of leads you into the mitigation stage. So once you have a subset of data points that you know is disproportionately impacted, I suspect it's not an either or. So data augmentation, as we all know, is still a powerful way to amplify what is really underrepresentation. This is the long tail. So if it's an underrepresented frequency point, the hope is very responsive data augmentation or additional data collection will mitigate some of that. On the other hand, articulating the impact and surfacing these as the most disproportionately impacted offers very cool avenues for optimization and mitigation. So I feel like this was in many ways establishing the problem and establishing not just a problem, but a framework in which you can surface a subset to mitigate. The downstream research directions of this are that pruning is in itself an optimization choice. And right now, our optimization choices don't encode any particular upweighting or downweighting of the long tail or constraint on how to treat it. But once you know what is impacted, it opens up a whole host of avenues on how to constrain that treatment. So that's also very important because optimization needs a framework and we can't pre-specify. A lot of it is how do we cheaply automatically surface constraints. This relates back to what I mentioned earlier, and I believe it was Sayak asked this question of how do you treat all these weights? And I brought up this idea that it appears most of the weights in our network, and this is something I think is an exciting future research direction, are being used to encode the long tail in a very expensive way. The other thing we get once we surface what is impacted is that we can treat it differently early on in training. And so maybe we don't even need all these weights because if we can pre-identify or early signal identify what is impacted, most machine learning people can already automatically start thinking of a host of ways to leverage that information in a way that you don't need capacity to solve it.
It's really interesting because on this subject of interpretability in general, it's so difficult, isn't it? Because we have these really complicated deep learning models. And you said yourself, many of the interpretability methods are no better than random guessing. And we will never understand their behavior. And all we can do is we can do tests after the fact. We can do data grouping and counterfactual examples. And you said yourself, sometimes we don't even have the categories, but we have the data and we sample from the categories and we have these priors and then we can measure the fairness afterwards. There's a very weird relationship and we don't really know what kind of relationship there is between the priors and the categories and the data and how that works out. So it just seems, one argument, by the way, is that having a sparse network is a good thing, right? Because it makes it, even though it might be more discriminatory, at least it's more understandable. Having this long tail, does that just make it even less understandable?
That's a dangerous argument. So I guess there was a few things packed in there. So one was a reference to this paper, which was a separate paper, a benchmark on interpretability methods, and it was focused on saliency methods. So these are single image explanations. These are very widely used, particularly in computer vision, where you look at the ranking of what was important for a single image in a given prediction. And there, the takeaway of that paper, which I did with colleagues at Brain, was that some of these rankings are no better an estimate of what's important than just a random guess. And in many ways, a lot of my research since has been how do we move away from these single image explanations to instead automatically surfacing slices of the distribution which are treated by the model as more challenging. And I suspect we will fare better there for a few reasons. A lot of our understanding of what's important is relative. Like a lot of how we process the world is by understanding what is different. If you were told to stay at home, but all of your neighbors were allowed to go out and experience their normal days, you would probably feel much more like that wasn't a satisfying explanation of why you had to stay at home during COVID, but everyone else had to go out. Whereas because everyone's being asked to stay at home, we're much more willing to accept that as a reasonable explanation. So a lot of our understanding of what is reasonable as an explanation is a relative understanding, whereas saliency maps, by definition, only provide a single explanation. So you look at a saliency map and perhaps you squint and you're like, does that mean my model's off? It's hard to tell, actually, without looking at a million saliency maps, whether the saliency map was particularly odd for this class. So both the research on compression, which is surfacing the subset impacted, as well as recent work I've done on leveraging the variance of gradients to surface what is hard to learn early in training, have been more about, let's actually try and surface slices of the distribution automatically for humans to assess and get a sense of the decision boundary. And there I am far more optimistic about interpretability because it allows humans to gain a flavor of the decision boundary, because it allows them to select parts from different slices of the distribution, but also to prod and to think about, how does this map to my own understanding of what would be challenging for this task? At the end, you made a fairly, I would say, it's a fun talking point, which is what you said was, is the fairness, perhaps I'm capturing it correctly, but is the fairness implications, does it worth, how does that weigh against our need for compression? So I think that it's not clear that these are desirable properties that need to be treated in isolation. And partly what that paper was getting at was that once what is disproportionately impacted, you can still achieve very high levels of compression while constraining the model to just redistribute some of that pain point a little bit better. So in many ways, because these fields have been treated in isolation, it's often seen as a zero-sum game. But in fact, partly what was fun about this paper is we show it's not. Once you realize what is disproportionately impacted, you can change the optimization process, redistribute how these weights are placing emphasis, and you can in fact, what was surprising is that we're partly suggesting you can easily fulfill multiple constraints. And that is a fun area of future research. And partly what I was mentioning to Yannic is that identifying disparate harm and mechanisms that cause disparate harm is really, while it may sound intuitive, it's actually the first necessary step from an optimization process to mitigating, because you need automatic ways to surface. Part of our bottleneck in this regard has been that we've focused so much on having the labels existing, a human doing various metrics of false positive rate. We need instead automatic pipelines to think about what is surfaced and then go on to the mitigation stage.
I absolutely love what you're saying. And so maybe I want to rephrase a bit. And you said we don't always have the labels, but we have these methods that can automatically surface what kind of, as I see it, let's say we do a simple experiment. We compress a network. We see at which samples, at which slices of the distribution, does it really degrade? Which means these slices are naturally the ones that maybe underrepresented, whatnot. So could you imagine a future where, because these attributes, these protected attributes, they're very human, right? We go there and we say, we don't want this, we want this. They're often binary. They often neglect the complex nature of the world and their intersections and so on. Could these methods be a way forward where we do away with sort of these human-created protected attributes and say, we just have methods that tell us where our networks are bad as of now, and all we're doing is we're trying to get them better on that?
Yeah, I suspect it's a combination of both. So the reason, partly why we can't go away from the binary attributes, a lot of fairness research is focused on these binary attributes. And I agree that by their very definition as binary, they miss a lot of the complexity of the human condition. A lot of the reason why the focus has been on these is because of our legal framework. So it's very interesting because the same way so much of the work on interpretability focused on saliency maps, the single explanation, a lot of that was because of the right to explain, and people were really focused on single explanations. So there's an implicit hand in the research here, which is being shaped by the existing legal framework and what researchers are trying to do as tools for the legal framework. But taking a step back, I, as a researcher, am far more excited about this idea of surfacing what is more impacted, because the truth is, and this goes back to the idea of the human condition, the notion of what is an identity which is disadvantaged versus identity which is advantaged is susceptible to our changing history. And so in many ways, these boundaries, like comedy, they change over time. What we find funny at one point is no longer funny a mere few years later. And so having tooling which doesn't hard code preferences, but surfaces what is higher priority for human-oriented inspection is the area of research that I've always been more interested in, because I suspect in many ways what you're trying to capture is a fusive nature of where on a human decision boundary as a society do we currently agree that we don't want machine learning amplifying certain notions of bias, which makes it such an interesting area to work in, because it's so hard to codify these notions of human judgment, and it's in flux. To your point, the binary definitions we have today are fairly crude, and so are likely to change as our society changes.
So let me make my last question a bit cynical.
Excellent. I appreciate
given
that.
You have these methods that surface, you say we have methods that surface where we currently have like underrepresentation or bias or anything like this. On the other hand, there is like this slight implicit assumption in there that technically the problem is equally easy or hard on the whole distribution. And whenever our method surfaces that these samples over here, performance deteriorates when we squeeze or something like this, that must mean they are somehow underrepresented or biased. How do you differentiate between something that is underrepresented or biased against from something where legitimately the problem is a harder problem and therefore a neural network has a harder time maybe learning it?
I don't, because I think it's actually very intertwined. So we've talked here in this context about protected attributes being in the long tail, and that's often related just to the frequency of those protected attributes being present in the data set, and the model having the capacity to treat those long tail in a way that it encodes a useful representation, but also in the long tail, often challenging examples and noisy examples. So to your point, you mentioned difficult. So a lot of the examples which surface when you prune are fine-grained classification tasks. I'll move it to another data set. So for the fairness data set, we looked at celeb A. Tim mentioned the blonde males example that we looked at. It was the most underrepresented group in that data set, and we showed that it was disproportionately impacted. But if you move to a data set like ImageNet, a lot of what gets captured in the long tail is images which are very close to the decision boundary between two classes. And to your point, these are just intrinsically more difficult images to classify because even for a human, in fact, we support this with a human study and we show humans have difficulty. And then there's, of course, noisy examples. So noisy examples would be mislabeled or improperly structured. So while you are surfacing the long tail, the suggestion is not that this is just your protected attributes. It's the series, it's the slice of data the model has the hardest time learning and has thus used a ton of parameters to encode performance on and to memorize, essentially. The notions I'm talking about are very linked to the examples that the model needs to memorize, because that's why when you take away 90% of capacity, that's why these are the examples you lose performance on, because the model has essentially decided, I can't extract a useful representation of these examples. I'm just going to spend a ton of parameters encoding what is a memorized mapping of this particular example. But yes, very good point. Very good clarification.
Amazing. Well,
and not cynical. I thought that was an excellent question.
I'm going to finish off by asking you about Anna Karenina. So you said in your paper that happy families are happy in the same way and unhappy families are unhappy in their own way. And of course, this was Tolstoy's observation that it takes many different things for a marriage to be happy, whether it's financial stability and chemistry and shared values and so on. But any one of those aspects not going right could result in an unhappy marriage?
Yeah, it's very interesting. So my background is very typical. I'm kind of rogue at brain. I didn't do the formal PhD in machine learning route. And I did economics. I love history. I did a brute force route I taught myself both machine learning and coding. And my whole career has been choosing questions that I'm really curious about and brute force diving into them. Yes, I think you probably see this throughout the paper, but I not just mention Tolstoy, but I also kind of weave in all these quotes in different places. I also talk about really the record player as another example of technology repurposed for unusual means. So it's definitely perhaps what makes this a more eccentric paper to read, but it's also the connections I love drawing. I think a lot of why I've enjoyed research in machine learning so much is that it's partly connecting fields. In many ways, this last paper we talked about is a great example of that. I'm connecting compression, which is typically thought of in terms of test set accuracy, to all these different areas, thinking about fairness. So yes, I'm a fan of literature in general, and I loved weaving it into this paper.
Amazing. It was a fantastic paper.
If I may suggest just one little point, if I may suggest. So because of all of this literature tenor that you have showcased in your paper, I felt while reading the paper, there's this poetry in motion going on, and I'll have to be totally honest about that.
Amazing.
Thank you.
Sara Hooker, thank you so much for coming on the show. We really appreciate it. It's been an absolute honor. And yeah, just keep doing what you're doing.
This has been so lovely for me. I've been a fan of the show, so it's really fun to get to chat with all of you. And I really enjoyed the combination of excellent, really grounded historical questions and the slightly cynical one, as Yannic says. So it's been wonderful. Thank you.
Thank you so much.